minimize this. All right, well, while people are joining, I'm going to share this screen. All right, let's see if I can erase this. Okay, so while people are joining, let me do a little recap of what I covered so far. So, started talking about chapter 19, vibrations and waves. Started off with just a general description of what a wave is. A wave is just a traveling disturbance that's traveling through some medium. So in a wave on a string, the disturbance is just the string moving up and down, while the wave is actually the disturbance which is moving, in this case, horizontally. Talked about two main kinds of waves. One is called a transverse wave. The other one's called a longitudinal wave. So real quick, a transverse wave is one in which the disturbance is perpendicular to the direction of travel of the wave. So let me show you that on a different screen. PowerPoint slides, lecture notes, Zoom. Oh, there. And let me move this. So many types of waves. Okay, so in terms of traveling waves, this wave I'm showing you right now is a transverse traveling wave. So here the wave is actually moving to the right. Can everybody see this transverse traveling wave? Somebody give me a thumbs up if you can see it.
Yes, we see it.
Okay, so a transverse wave is one in which the medium, which in this case is the string, is moving up and down. That's the direction of the disturbance, but the wave is actually traveling to the right. So this is sort of the typical wave that most people are used to thinking about. There's also a longitudinal wave, which is at the bottom. And in a longitudinal wave here, this might be like a wave on a slinky or something like that. If I look, any one little piece of this slinky is just moving back and forth. That's the disturbance. And the direction of travel of this particular wave is horizontal. So in this case, the wave is being disturbed along the same direction the wave is traveling. That's what we call a longitudinal wave. Stop that. Go back to. Okay, and then for waves, there's some specific things that we use to describe a wave. So one, the big things are amplitude, wavelength, frequency, period, crest, and trough. So let me highlight this. Let's use red. No, let's use blue. So wavelength, in a sense, is how long the wave is. We measure the wavelength from either the highest point to the next highest point. So crest to crest. You can measure the wavelength from lowest point to the next lowest point, which would be trough to trough. Or a wave is also one complete up, down, and back motion. So this would also indicate the wavelength. Amplitude, in a sense, is how tall the wave is. And we always measure the amplitude from the middle of the wave to the highest point, or the middle of the wave to the lowest point. It is not the distance from the highest point to the lowest point. That would actually be twice the amplitude. All waves are created by some object which is oscillating up and down. In terms of voice, it's your vocal cord oscillating back and forth. If I'm making a wave on a string, I would be the one creating the wave. Frequency is basically how many vibrations whatever's creating the wave makes every second, or another way of thinking about it is how many waves pass a given point every second. So let me go back to this. So let's just say that I was standing right here at this position where the arrow is, my cursor. If I were to count how many waves went by me every second, that's what the frequency would be. Let me mute everybody for a second. Alt tab. Lecture. Hold on 1 second. Stop this share. I'm gonna mute everybody. Mute all. Okay. And so period is basically how long it takes for one complete oscillation. But the big equation I want to talk about right now is just this wavelength times frequency equals wave speed. This is the big equation that applies for all kinds of waves. And this equation sort of makes it look like that if I were to increase, let's say, the frequency of a wave, then that would result in the wave speed increasing. And that's not the case. Wave speed is a constant that only depends upon the properties of the medium that the wave is traveling through. So for sound, the speed of sound depends upon temperature. At a given temperature, all sound waves travel at the same speed. So the wave speed is a fixed number that only depends upon properties of the medium. For a string, it depends upon what's called the linear mass density of the string, basically how heavy it is compared to how long it is. And it also depends upon the tension in the string. Now, what determines the frequency? What determines the amplitude? All waves are created by something which is oscillating up and down. So if I were creating a waves on a string, I control the amplitude by how high I move my hand up and down, and I would control the frequency by how quickly I would be oscillating the string back and forth. So the big thing here is if the frequency of a wave goes up, the wavelength of the wave would go down, but the speed is constant. Now, one thing to keep in mind, if wave speed depended upon frequency, then listening to music would be a whole different experience, because let's say you go to a concert, you want all the different sounds from all the different instruments to arrive to you at the same time. If different frequencies traveled at different wave speeds, then you might hear the guitar at a different time than you hear the bass at a different time than you hear the singer, and so on. Last thing we talked about was that, unlike physical objects, waves can exist at the same place at the same time. When they do, they undergo something called interference. And basically what you end up doing is you just add the two waves together at every single point. So if I could imagine these two waves existing at the same point in space at the same time, there's no easy way to draw it. But if when one wave is at a maximum, the other one is at a maximum, and when one's at a minimum, the other one's at a minimum, the end result is when you add those two waves together, you're going to get a bigger wave. We call that constructive interference. The end result is going to be a wave with a bigger amplitude. On the other hand, if you have two waves that are kind of mirror images of each other, so that when one wave is at a maximum, the other one is at a minimum, and the one is at a minimum, the other one's at a maximum, those two waves would cancel each other out. We call that destructive interference. And if we're talking about sound, constructive interference would result in a louder sound. Destructive interference would result in either a much lower sound or no sound at all. And if anyone has a nice pair of noise canceling headphones, this is how they work, is basically you've got every set of noise canceling headphones actually has a microphone on it. And what it's doing is it's recording the outside noise, and then the circuitry inside the headphones is basically taking that sound and we're flipping it upside down and then sending it into your headphones at the same time you're hearing the outside noise. And what you're basically getting is destructive interference. Those two sound waves canceling out, resulting in no sound. And that's kind of what I got to. Today we're going to cover standing waves and Doppler effect, and I'm going to go into chapter 20. But what I want to do is stop, pause, and see if there's any questions on anything I've covered so far in chapter 19. If you have a question, throw up a hand, unmute yourself. If not, the recap is going to come off. Going once. Going twice. Sold for no dollars. All right, recap coming off. The brand new information hat coming on. And I want to try and do this. Let me see if I can do this on PowerPoint. PowerPoint. F5. Okay. Let's see if I can share this. Never tried this before. Well, maybe I have. Share screen. Uh, all right, can people see my PowerPoint presentation? And can they see the animations moving?
Yes.
Excellent. Okay, so again, here's just another example of a transverse wave. It would be a wave on a string. So in this case, the wave is being disturbed, the string is moving up and down, and the wave itself is traveling to the right. This is a transverse wave. Longitudinal wave is one in which the disturbance and the direction of travel are along the same direction. So here, the slinky is being disturbed, let's say left and right, and the direction of travel of this wave would be to the right. This would be a longitudinal wave. Let's cut through all that. So again, interference. Two waves existing at the same place at the same time. What I do is basically add those two waves together. So in this case, I got one wave moving to the right, another wave moving to the left. When they exist at the same place at the same time, what I would do is if I want to know what is the result here, I would add this wave, whoops, move that, and this wave together, and this would be the result mathematically, is adding these two waves together. Or right here, I add this wave and this wave together, and this is the result. You don't need to know that mathematically, but two waves at the same place at the same time will interfere with each other. The end result could either be a bigger wave, so this would be my constructive interference, and this is more like a pulse rather than a wave. But I could also have these two waves canceling each other out, and this would be destructive interference. So again, constructive interference, bigger wave, destructive interference, smaller wave. And the other cool thing is that when the waves interfere with each other, they do not continue to affect the motion after they are no longer in the same place at the same time. So these are just two different sets of animations of waves traveling in opposite directions. When they're in the same place at the same time, they interfere with each other. But after that, they continue moving along their merry way as if nothing had ever happened. Okay, so what I want to talk about now is a really cool thing called standing waves. And let me first introduce this by saying, let's say I sent a wave down a string, and one end of the string was sort of tied to a wall or something where it was too rigid to move. What's going to end up happening is when that wave hits the boundary, it'll do what's called reflect. So that wave will reflect back the other direction. And for mathematical reasons I won't go into, when it reflects, it actually inverts upside down. So you see this wave coming in, hits the wall, reflects back, but when it reflects back, it sort of reverses upside down. Now this is just a single pulse. If instead I created a series of pulses, I had a bunch of waves coming down, they hit the wall, and then they start to reflect back. What I'm going to have are two sets of waves traveling in two different directions. I think my camera reverses its image, so I have to do it this way. So you've got a wave coming in, hits the wall, and then I'm going to have another sets of waves traveling in opposite directions. Those two waves can interfere with each other. And what you'll see is these two sets of waves traveling in opposite directions. If I get the frequencies just right, I can create what's called a standing wave. So let me just pause for 1 second. Actually, we just do a new share. Go back to Okay, so right now, the waves that you're seeing, top wave is a transverse wave, the bottom one's a longitudinal wave. If you imagine I had a wall right here, then these waves would hit the wall, reflect backwards, and I would have two sets of waves traveling in opposite directions. If I got those waves just right, I could create what's called a standing wave. In a standing wave, what it really is, and this is super cool, is it's two sets of waves traveling in opposite directions that are always producing constructive and destructive interference at the exact same point. So like right here, this little red dot, this is what's called a node. And I'll go into this in a second, but this is where destructive interference is always happening. Here, if you notice, this point is not moving at all. Basically, I'm getting destructive interference happening at that point. Can I move this position a bit? Right now, I have the red dot on what's called the antinode. It's where I have a maximum amplitude, and that's where constructive interference is happening. So what you'll see, formation. Okay, so let's let this animation restart. And I really wish I could have shown you this demo in class because it's badass. Give it a second. So imagine I'm sending a series of waves and here's a wall. These waves are going to hit the wall and reflect. And those reflected waves are then going to interfere with the waves that are already moving. And if I get the frequencies just right, I create what's called a standing wave. It's a standing wave because it appears not to be moving left or right, just oscillating up and down. So again, I'll let this run one more time. So like right here is a node, a node, a node. Antinode is where I have maximum amplitude happening. And what's really cool about this is a standing wave is what you would see in blue. What I've marked right here is where I have destructive interference happening between the two waves. This little dot here is where I have constructive interference. So what you see when you see a standing wave is in blue. But what's really happening is this blue wave, which is oscillating up and down, really consists of two waves traveling in opposite directions that are producing interference in just the right way that you get this standing wave. And standing waves can happen at certain frequencies. So the very first standing wave that you can create just has one segment, and that one segment oscillates up and down. If I then increase the frequency, I can get what's called the second standing wave, which is the second harmonic. If I then continue to increase the frequency, I could get the third harmonic and so on. There was another formation standing wave. No. Okay, so like here, this would be the very first standing wave that you could create. And we call that the very first harmonic fundamental frequency. If I were to then increase the frequency, what I could get is the second harmonic. And basically, I think of these as just how many little segments there are. The first harmonic, just one segment oscillating up and down. Second harmonic, I've got two segments oscillating up and down. Third harmonic, I've got three segments oscillating up and down, and so on. Okay, so going back to this PowerPoint, which one's PowerPoint? So what you see as a standing wave, like I said, is two sets of waves. I have one set of waves, let's say the waves are coming from the right, they hit some wall, and then I have a second set of waves from the reflected waves traveling in opposite directions. Then they can produce interference, and if we get the frequency set up just right, what you'll see are these standing waves. And again, standing waves can happen at different frequencies, and those frequencies are going to depend upon certain properties of the string we're not going to worry about. But a few things in terms of language. An antinode. This is a region where the amplitude is a maximum. So this is the max amplitude. And so this right here would be an antinode. This right here would be an antinode. This right here would be an antinode. This is where the string is moving up and down the most, is where constructive interference happens. A node, I think about node as no amplitude. This is where fully destructive interference is happening. The two waves cancel each other out. So this right here would be a node. This right here would be a node. This right here would be a node. That right there would be a node. Okay, let me pause this for 1 second. Stop share. I tried to show you an animation. No, 1 sec. Animations. Standing waves. Hold on. Grab that. All right, question.
What's happening in real life when there's a standing wave? Like, what does that look like to us?
I was just going to show you a couple animations. So one, all music is pretty much being formed by standing waves. So when you pluck a guitar, even though you can't see it, you're actually setting up standing waves on the guitar. Or if you were to do a musical instrument, like a flute or something like that, you can actually get standing air waves set up within the column. So let me show you a video or two. Okay, so one, I don't know if you guys have ever seen these before, but you can put an iPhone in a guitar, and then when you pluck the strings of the guitar, you can get a standing wave formed. So let me see if I can play this. Now, it's a little bit more complicated because this also has to do with the way that iPhones shoot videos and how often they refresh. But let me, this is the demo that I would have shown you in class, and it's a really great demo. It's cool because I can use a strobe light to make the wave look like it freezes.
Frequency generator is connected to what's called a wave driver. It's just a speaker. It's going to pump up and down.
So let me move this ahead.
They're not exhibiting consistent.
So like here right now would be a standing wave. Second harmonic. This right there is a node.
That's sent down. And
here's an antinode.
Constructively interferes with the next.
So let me pause this for 1 second. So what's happening is there's a little basically wave vibrator, little mechanical device here, which is just moving the string up and down. That's sending a wave on the string, which is moving, in this case, to the right. Then the string is tied up right here, and it can't bounce up and down. And so when the wave hits it, it reflects back. So what you get are two sets of waves traveling in opposite directions. But if I get the frequencies of these waves set up just right, then I can always get constructive interference happening at certain points called antinodes, destructive interference happening at certain points called nodes.
Next wave that comes down right at this point.
So let's see.
Now the waves that reflect, that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still works.
And let me move
A
forward.
string that's held.
So this is the very first standing wave that you can set up. We call it the fundamental frequency.
So again, third.
So this is the third harmonic.
You can see in high speed. So check out this shot with the high speed camera and verify for yourself that it is 1 1/2 wavelengths.
Pause that for a second. So here it's kind of interesting. This is just being filmed at a very high speed. And again, it just looks like I've got this string just oscillating up and down. But keep in mind, what's really happening is I have one set of waves coming from one side, one set of waves coming from the other side, and they're producing interference at specific spots. So as this thing is oscillating up and down, this spot right here would be a node. This spot over here would be a node. Okay, again, so let me just go back to this types of waves. So again, like for a traveling wave, this right here would be from two different waves traveling in opposite directions and interfering in just the right way to always produce constructive interference right here, called a node. And let's see if I can move this to an antinode. I'm sorry, that's an antinode here where I have the maximum amplitude. And let me move this to a node, marked position. That's not quite it. This is close to a node. I don't have it exactly right, but this is not really moving up and down very much. All right, let me pause this for 1 second. What questions can I answer about standing waves? Things to know about standing waves are, it's from two waves traveling in opposite directions that interfere. The regions where I have destructive interference is called a node. That's basically where there is no amplitude. And then the regions where I get fully constructive interference, I have something with a bigger amplitude, is called the antinode. Questions about that? All right, last topic for chapter 19 is all about the Doppler effect. So let me actually do this using PowerPoint. Okay, so little question for you. Let's say that you are a bug and you are bobbing up and down in the middle of a puddle of water. Or let's just say that you're a bug and you're doing push-ups. Every time you basically dip into the water, you're going to produce this water wave that's going to move outwards. Now, if the bug is not moving, then it doesn't matter if I'm on this side of the bug or this side of the bug. I'm going to detect the exact same frequency of waves that the bug is producing. So if the bug is moving up and down, let's say a couple times a second, frequency is 2 Hertz. That's going to be the same as the frequency of the wave that I detect on either side if this bug is not moving. Now, what happens if the bug is moving while it's doing its push-ups or creating a wave? Then what happens is, depending upon whether the bug is moving towards me or away from me, I'm going to detect a different frequency than the bug is emitting. So let's say the bug in this case is moving to the right, and they're moving towards observer B. And moving, he's not unhappy. Let me do that again. He's taking physics. He's fucking stoked. Oh. Excuse my language. All right, so we've got this bug, which is producing waves. Before, we were considering the bug not moving. And so if the bug is not moving, it doesn't matter which side of the bug I'm on, I'm going to detect the waves at the same frequency that the bug is emitting them. But if the bug is moving, if it's moving towards me, so let's say I'm observer B, what's going to end up happening, notice 2 things. One, since the bug is moving towards the waves it's already produced, the wavelength is actually smaller. I could consider the wavelength, let me go back one more time, to be the distance between any 2 sort of circles here. And if I'm on either side, the wavelength that the bug is producing and the wavelength that I detect are the same. But when the bug is moving, or let's just be specific, any source of waves, when that source of waves is moving, you're going to detect a different frequency than it emits if it's moving towards you or moving away from you. So observer B, where the source of the waves is moving towards them, they are going to detect a smaller wavelength, but a higher frequency. So you can kind of see these 2 little, the distance between the 2 circles, that would be the same thing as the wavelength. It's smaller if it's moving towards B, but if you notice for A, what they're going to detect is a higher wavelength, a bigger wavelength, but a smaller frequency. This is what we call basically the Doppler effect. Is if a sound source, let's just be specific about sound. If a source of sound is moving towards an observer, they're going to detect and measure a higher frequency than the bug is emitting. If it's moving away from the observer, they're going to detect a lower frequency. And we'll get to this next chapter. Sound is related to pitch. So a higher pitched sound is a sound that has a higher frequency. A lower pitched sound is one that has a lower frequency. So if the bug is moving towards me, I'm going to detect a higher frequency. And if the bug is moving away from me, I'm going to detect a lower frequency. So sound source moving towards you, you detect higher frequency. Sound source moving away from you, you detect lower frequency. So you don't need to worry about this formal definition, but Doppler effect is the change in frequency measured by an observer because either the source of the waves or the receiver is moving. So generally, we're thinking about the Doppler effect as like, let's say, a siren from a fire truck or a police car or something moving towards us and then passing us. When it's moving towards us, we detect a higher pitch, a higher frequency, and then when it passes us and starts moving away from us, the pitch is now decreased. We detect a lower frequency. So this is, like I said, is why you hear the frequency of a horn change when it passes you. As it's moving towards you, you detect a higher frequency, smaller wavelength. When it passes you, you detect a lower frequency, a higher wavelength. So again, let's look at this. Let's just say that this fire truck is emitting sound. It's got its siren on, but it's at rest. If it's at rest, it doesn't matter which side of the fire truck you're on. You're going to detect the exact same frequency that it's emitting. However, if the truck is moving, like in this case, the truck is moving to the right, then if it's moving towards you, what's going to end up happening is those waves are going to start to get compressed because it's moving in the same direction of the waves it's already produced. And I'm going to end up with a smaller wavelength, a bigger frequency. However, if it's moving away from you, then in a sense, it's starting to outrun the waves it's already produced. The end result is you're going to detect a larger wavelength, smaller frequency. So the thing to remember about Doppler effect is when the source of sound is moving towards you, you end up hearing a higher pitch. Basically, the frequency increases. When the source of sound is moving away from you, that's when you detect a lower pitch because the frequency decreases. Now that's if the source of the sound is moving towards or away from you. The question is, could the same thing happen if the source of the sound was stationary and you were moving? And the answer is yes. Don't worry about these V0 T's and stuff like that. But let's just say I had a speaker and I could run fast enough either towards or away from the speaker. Well, we're not going to do the mathematics of this, but the Doppler effect, how much the frequency shifts, depends upon how fast you're moving, how fast the sound source is moving. If the sound source is stationary and you're moving, you're going to have to be moving pretty damn fast to actually detect it. But if you were in a car that could go hundreds of miles an hour, doesn't even have to go hundreds of miles an hour, but 50, 60 miles an hour. Well, sorry, if you were in a car, yeah, let's say I had a stationary speaker and you could drive past the speaker, you would see that as you are approaching the sound source, you're going to detect a greater frequency. As you're moving away from the sound source, you're going to detect a smaller frequency. So when the observer is moving towards the source, again, a greater frequency, greater pitch. When the observer is moving away from the source, they detect a smaller frequency. Now, let me just stop this. Let's do a new share for a second. Simulations, this one, Doppler effect, Okay, let's look at this another way. So let's just say I've got this sound source, and again, it's not moving, so it doesn't depend on where I am. If I'm right here, or right here, or right here, or right here, I'm going to detect the exact same frequency that it's emitting. But if it starts moving, so now it's moving half the speed of sound about, then it's going to start to catch up to the waves it's already produced. So if I'm right here in the same direction that it's moving towards, I'm going to detect a smaller wavelength, a bigger frequency. If, on the other hand, it's moving away from me, so I'm over here, then I'm going to detect a bigger wavelength, a smaller frequency. So keep in mind, moving towards you, higher frequency, smaller wavelength. Moving away from you, bigger wavelength, smaller frequency. Now here's the question. What happens if something's moving at the exact same speed of the waves that it's producing? So here's a case where I'm now moving at the exact same speed of sound. What you would see is these waves pile up on each other. In essence, I'm catching up with all the sound waves I've already produced. This results in what's called a shock wave. And if we're talking about sound, if you've heard of sonic boom, that basically happens when a plane is traveling at or faster than the speed of sound. These sound waves all pile up. Let me do this again. So let's move this at the speed of sound. These sound waves all pile up, and there's a tremendous amount of energy associated with these sound waves all interfering with each other. And a sonic boom can actually knock down trees. It can shatter windows. If we have time, I'll show you a YouTube video, but you can actually just do a search for sonic boom shattering windows, and they've had air shows where planes have flown too close to a building. They are going faster than the speed of sound. The sonic boom, the shock wave, will literally knock out all of the windows in a building. It's pretty crazy. Now, here's the question. What happens if I'm going faster than the speed of sound? So have you ever heard of like Mach 1, Mach 2? Mach is just how many times the speed of sound. So if you had a plane that was actually flying at Mach 1 or Mach 2, that would be it's flying at the speed of sound or twice the speed of sound or so forth. So if you're traveling faster than that, so here's something which is traveling 1.28 times the speed of sound, 1.3. You start to outrun all of the waves you've already produced. The end result is you get this characteristic V sort of shape behind the aircraft or boat or something like that. In a mathematical course, this is pretty cool. If you measure the angle of this V, you could actually calculate how fast the object is moving relative to the speed of sound. But again, anytime you have something traveling faster than the speed of the waves it's producing, you get this characteristic V shape behind it. We call that a bow wave. And it's all of these waves that are piling up on each other. So in a boat, let me stop this for 1 second and do a little white screen. In a boat, if you're ever in the water and you see, so let's say this boat is moving this way, you sort of see this characteristic V wave behind a boat. This is called a bow wave. And it only happens when whatever's producing the wave is moving faster than the wave speed. So like for a boat, water waves have a certain speed. If the boat is traveling faster than the speed of the waves in the water, then those waves start to pile up on each other, kind of like I showed you for a sonic boom, and you get what's called a bow wave. So this happens when, if we're talking about water, boat is traveling faster than the waves. If we're talking about sound, the bow wave behind, let's say, a supersonic jet creates what's called a sonic boom, and it's all of these sound waves piling up on each other. And let me share one more time my PowerPoint. F5, come on, F5. Okay, so bow wave is sort of this V-shaped wave produced by an object which is traveling faster than the wave speed. So this happens, like I said, in a boat. Anytime you see a V shape behind the boat, you know that that boat is traveling faster than the speed of waves in the water. If we're talking about a plane, then that produces a shock wave. It has a tremendous amount of energy associated with it. And when that shock wave hits the ground, it has a tremendous amount of force and energy. It can knock trees down. It can blow out windows. Because of that, there's limits to where planes can actually fly faster than the speed of sound. You can't do that over a residential area. So what I want to quickly show you is this really cool video, couple of sonic booms. This is the
Sorry, Joe, I have a quick question. So the sonic boom and the shock wave is the same thing?
Yes. So sonic boom is, well, a shock wave happens anytime something is traveling faster than the speed of waves in the material. A sonic boom is specifically for sound. So like you can actually have a shock wave with light, you can have a shock wave of a bullet passing through, but in terms of sound, The shock wave produced by something moving faster than the speed of sound is called a sonic boom. So yes, they're the same thing, but a sonic boom is specific to something traveling faster than the speed of sound. You can have shock waves that don't have anything to do with sound. And then, I won't touch on that real quick. So let me see if I can keep the annotations, discard. I want to start a video and show it to you and see if that works. Mach 1, open with VLC player. Okay, so this, let me make this bigger and then share it with you. New share. Okay, so this is a very cool video. This is a plane which is flying by a bunch of people on the water, and the plane is moving faster than the speed of sound. And what's happening is this plane is producing a shock wave, one which is pretty cool. Notice where the smoke, or this is not really smoke, but notice where the cloud is forming. It's got nothing to do with exhaust from the back. Basically, if you notice, it's starting to form right up here. What's happening is this plane, this is really pretty cool. So one, you are not seeing the shock wave. Kind of interesting. You don't need to worry about the physics behind this, but the shock wave is right in front that you can't see. What's happening is right behind the shock wave, the sonic boom, there's all of this energy with all these waves piled up right on top of each other. But right behind the sonic boom, you have a region of cold temperature, without going into all the physics, just where the sonic boom is, where the shock wave is, right behind it, the temperature is lower. That lower temperature causes the water vapor in the air to condense. So what you're seeing as this plane flies by is the region right behind the shock wave where the temperature, so the shock wave might be right here, but the shock wave right behind it has a region of lower temperature. That causes the air vapor, the water vapor in the air to condense. So what you're seeing is right behind the sonic boom where the temperature has dropped. So cool. Now, this is a really rare video. Conditions have to be just right. You have to have something which is traveling faster than the speed of sound, somewhere where there's a lot of humidity so that when the temperature drops, you can get this sort of cloud forming. And let me just show you one more picture has stopped. This is, let me share this one. Here's a plane that's actually breaking the sound barrier, driving past some people on a ship. And you can sort of hear what the sonic boom sounds like. So a couple cool things about this. One, you can hear, you can't see the air forming into water vapor like you did before. It doesn't mean there's not a shock wave. It's just that the humidity where this plane is flying past is not great enough so that there's not enough water vapor in the air to form basically these little clouds. But it's kind of cool. You can see where this is hitting the water. So you can't, again, you can't visually see the shock wave and there's not enough humidity to form these little clouds behind it, but you can see where the shock wave is actually hitting the water right below the plane. All right, I'll pause there for a second. That's kind of the end of chapter 19. I want to touch maybe, what time is it? No, 10:15. What I want to do is maybe spend another 10 minutes in lecture portion just introducing chapter 20. But before I do, I want to pause and see if there's any questions I can answer on anything from chapter 19. Questions? Everything sound good? Yeah, Joe, it sounds great. I can't wait. Let's go on to chapter 20.
Sounds great, Joe.
All right. Actually, you know what? let me do a couple clicker questions. Okay, let's take a look at just a few quick clicker questions. So I didn't share this. Let me share it. Share screen. Okay, so question 6 says, in the standing wave shown, what is the amplitude? And actually, I have a couple questions for you in terms of this. So for this question, what is the amplitude? But I also want to know how many nodes are there in this standing wave and how many antinodes?
All together or each?
All together. So take just 15, take 15 seconds. What is the amplitude of this standing wave? How many nodes are there? How many antinodes? And then if you want, what is the wavelength of this standing wave? But I really want to concentrate on the amplitude. How many nodes? How many antinodes? And actually, let me just try this one more time for a poll. I want to do that. Alt tab. All right, anyway, it's not letting me start a poll right now. Let's just go through this. So 1, the amplitude is always the distance from sort of the middle of the wave to the highest point, or the middle of the wave to the lowest point. So they gave us from the highest point to the lowest point. That's actually twice the amplitude. So if this distance right here is 20 centimeters, then that means the amplitude is actually half of that. So the amplitude would be only 10 centimeters. Now, in terms of nodes and antinodes, a node, I think of node, no amplitude. It's where there's destructive interference happening where the amplitude is 0. So in this case, I have 1, 2, 3, 4, 5, 6 nodes. Now, one of your homework questions asks something like, how many nodes are there not including the endpoints? Normally, you would include the endpoints. So like here, 1, 2, 3, 4, 5, 6. But if the question was specific and said how many nodes not including the endpoints for this particular wave, the answer would be 4. And then how many antinodes? Antinodes are when you have a maximum amplitude. So antinode would be sort of right here. Here's 1, 2, 3, 4, 5. So in this case, the number of antinodes would be 5. I think that's it. Most of these are fine. Okay, so question or two? If not, I would just want to give you a little introduction to chapter 20 so I can finish it all on Thursday. Pretty quick chapter. All right, then let me open Physics 10, chapter 20 today, last week, Physics 19, 20. Uh-oh, technical difficulties. Chapter 20, recent, this PC. Let me try this one more time. I'm sure I started at chapter 20. New. Nope. Open. 1924. Oh, chapter 20. Okay. And let me do a quick share. Share screen. Okay. So let me just quickly deal with chapter 20. Just so you know, whenever I cover this live, chapter 19 and 20 are relatively short. So we do chapter 19 and 20 homework at the same time, quiz at the same time. So I'm going to just quickly start this, finish it on Thursday. Chapter 19 and 20 homework is due Friday, quiz on Saturday. And beats. I think, just to let you know, that I don't think I'm going to cover beats. Or at least maybe I'll touch on it, but it's one of those ones where it's really hard to do without a demo. I have tuning forks. I didn't think to bring every possible demonstration I could. So anyway, what we're going to focus on for sound is the beginning, the nature of sound, how sound is created, talk about speed of sound on different materials. Going to talk about interference. Basically, it's exactly the same thing. Sound waves can interfere just like anything else. And then we're going to spend some time talking about resonance. And I don't think I'm going to cover refraction of sound. So let me say I might cover beats. I'm going to see if I can find some videos online because I don't have the tuning forks here. So let's just take a quick little jump into sound for just about 5 minutes. So how is sound created? All sound is created by some object that vibrates back and forth. That vibrating object will create a pressure wave in air that travels through the air. And actually, let me just show you quickly what happens. Let me see if I have this PowerPoint for chapter 20. I do. Excellent. Oops. Escape that. I have to share screen. Okay, so remember, a longitudinal wave is one in which the disturbance is parallel or in the same direction as the direction of travel of the wave. So I showed you this animation before. This is a great animation that basically shows how all sound is produced. Something is oscillating back and forth. Could be your vocal cords, could be a string on a guitar, it could be the tines of a tuning fork. All sound is created by something which oscillates back and forth. What happens is when this thing, let's say, moves forward, it compresses the air, which creates a region of higher pressure. And then when it moves back, I get this region where there's less air of lower pressure. And it's the pressure wave of these air moving back and forth, which is actually traveling through the air. So when I'm talking, if you could somehow tag the air that's coming out of my mouth, it's not traveling from my throat to your ears. My vocal cords are causing the air in my mouth to oscillate back and forth, which causes the air around me to oscillate back and forth. And that oscillating air is then what travels outwards. So like a tuning fork, when they're called tines, when the tines of the tuning fork move farther apart like this, then they're compressing the air together, and I get this pressure wave of high pressure and low pressure, which travels outwards. Then, well, so what is a speaker? A speaker is just literally this little paper, it's called a diaphragm, that just moves back and forth because of the input from some kind of electronic signal. When it moves forward, it compresses the air together. When it moves backwards, it leaves this region of low pressure. You don't need to worry about these definitions, compressions, and rarefactions, but where the pressure is increased because the air is moved closer together, we call that a compression. Where it's decreased, we call it a rarefaction. So regions where I have a bunch of air pushed together is almost like if I took a slinky and moved all of the, I don't even know the things of the slinky, but you move them all closer together. I have a region of high pressure here. And then when I have a region of low pressure is where all the air is moved farther apart. And it's this pressure wave which ends up traveling through the air. Don't worry about that. But when that happens is, keep in mind, anytime there's a difference in pressure, there's going to be a force pushing from higher pressure to lower pressure. So inside of your ear, the pressure is at atmospheric pressure. But outside of your ear, that pressure changes whenever there's a sound, because sound is just this difference in pressure taking place in the air. And what happens is your eardrum moves whenever there's a difference in pressure on one side than the other. So, let's say here's your eardrum. And here's inside your head. Inside your head, you're basically at atmospheric pressure. However, if the pressure out here is not at atmospheric pressure, then there's going to be a force on your eardrum causing your eardrum to move. So let's say that there's a region of lower pressure. for a second? Well, there's always going to be a force pushing from higher pressure to lower pressure. So if the pressure outside your ear is less than the pressure inside your ear, there'll be a force moving your eardrum from higher pressure to lower pressure. If the air pressure outside your head is greater than it, so if I have a higher pressure, that's going to then result in a force on your eardrum in the opposite direction. So as these little differences in air pressure reach your ear, that's going to cause your eardrum to start to oscillate back and forth, depending upon whether the pressure outside your ear is greater than or less than your pressure inside. Well, the frequency that your eardrum moves back and forth is going to be the same as the frequency of the sound wave in the air. So here's a big picture of what's happening, and I'll stop here. Something is creating a sound wave by oscillating back and forth. In this case, it's a speaker. In the case of your voice, it's your vocal cords. That causes the air around it to start to sort of oscillate back and forth, and I have these regions of high pressure where the air is squeezed close together, low pressure where the air is farther apart. That pressure wave is what's actually traveling through the air, and then it gets to your eardrum. So just real quick, inside your ear, you've got, here's your eardrum. The pressure outside here changes depending upon the sound waves that are traveling through it. The pressure inside your head doesn't change. It's basically atmospheric pressure. So anytime there's a bigger pressure outside, pushes your eardrum in. Anytime there's a lower pressure outside, your eardrum is pushed out. So your eardrum is going to start to oscillate back and forth at whatever frequency the sound wave in the air is. Then what that does is there's little hairs inside your eardrum that start to move back and forth at whatever frequency your eardrum is. That vibrating hairs then send a signal to your brain that it then does what it does, and it interprets it as sound. Booyah! All right, let me stop this, discard, pause, stop share. Okay, that's just the little introduction I wanted to do to chapter 20. On Thursday, I'm pretty much going to finish chapter 20. What is it, 10:30, 9:30, 10:30? I'm going to stick around for about another 15 minutes, answer any questions people might have, but lecture portion of this is done. Done. Bring in office hours.